Hello everyone and welcome to the video on exponential functions with differentiation and integration. In other words, the calculus of the natural exponential function. This is really the time that it's kind of a big one. This is where we get to my favorite derivative and integration formulas. So I really like these ones. I think they're fun and they're excellent time to work on them. So I hope you feel the same. I know some of you are getting a little nervous right now about that, but don't be. These are actually really nice ones to deal with. So our objectives for this particular video: number one, we want to develop the properties of the natural exponential function. Number two, differentiate natural exponential functions. And number three, integrate the natural exponential function. Let's go and start out with a definition. The definition of the natural exponential function is that it is the inverse function of the natural log function, f of x equals ln x. And it's called the natural exponential function, is denoted by f inverse of x equals e to the x. Euler's number, okay? That is y equals e to the x if and only if x equals the natural log of y. Well, you probably remember this function. We dealt with this a lot last year. It does have a lot of interesting properties. You'll want to review those properties on page 347, but really it's really looking at, because it's an inverse, some of the things I do know in this case. Number one, that the domain is the real numbers. Let's get that negative sign there. Remember, the range of the log is all real numbers. So when we have an inverse, its domain is going to be the what was the range of the original, and therefore the range of this particular function is going to be from 0 to infinity. You'll also recall on this that this function, because it's the inverse of e to the natural log of x, the natural log of x is a continuous increasing function. This is also going to be a continuous increasing function, and you might remember the graph of this. Graphically, it's going to look something along this line here, and it's going to go through the point 1, 0. We'll put that'll be the point 1, 0. It's going to have a horizontal asymptote along the x-axis, curve up, and then go off. This function, it's continuous, it's increasing, and it is one-to-one. So we don't have to worry about it. We don't have to deal with that. It always has the inverse. And this one is concave up. So you'll want to, again, this kind of going through those properties pretty quick. And again, those are listed on the bottom of page 347, along with some exponent rules as well. But the other thing that you really want to be aware of on here is these inverse relationships right here. I know, because these are inverses, I know if I take the natural log of e to the x, it is going to be x. And the same thing, if I take e raised to the natural log of x, that will undo itself, and that will also give me x. And that relationship there can be helpful when solving some equations and functions later on. Let's take a look at solving the exponential function. In this case, the very first one I'm going to do is 4e to the 2x plus 5 equals 17. Now, when you solve an exponential function, the first thing you want to do is you do want to get the exponential here, in this case, the e to the 2x by itself. So to do that, I know I'm going to have to subtract 5 and then divide by 4. And so when I subtract the 5 from both sides, I will get 4e to the 2x equals 12. Divide by 4, and I get e to the 2x is equal to 3. Now to solve that, what I'm now going to have to do is because I want to solve it for x, I've got to get that 2x out of the exponent. And so what I'm going to do is use the inverse properties we just saw, and I'm going to take the natural log of both sides. So I'm going to take the natural log of e to the 2x equals the natural log of 3. By the inverse properties, the natural log of e to the 2x is just going to be 2x equals ln 3. And then to solve it for x, I divide by 2, so I get x equals the natural log of 3 divided by 2. That would be my solution on that one. What I'd like you to do right now is I would like you to pause the video, and I would like you to go and solve e to the 3x minus 1 equals 5. This is something that we did last year, so pause the video, see what you can come up with, and then when you get done, come back and we'll go through the solution on that problem. Well, when you solve this second problem, you should have got that x was equal to 1 plus the natural log of 5 divided by 3. Let's see how we did this one. In this case, this one right here is already solved. The exponential is already by itself, where over here it wasn't. We had the 4 and the plus 5. In this case, the 3 and the minus 1 are all part of the exponent, so I don't need to do anything yet with the 3 or the 1. To solve this. It's already solved for the exponential, so the very first thing I need to do is just take the natural log of both sides. So I have the natural log of e to the 3x minus 1 equals the natural log of 5. Well, in this case, again, by the inverse property, the natural log of e to the 3x minus 1 is just going to be 3x minus 1 equals the natural log of 5. And now I just go through and solve this one. So I'm going to add 1. Now, you can put it as natural log of 5 plus 1. I put it at the front just to eliminate the possible confusion of whether or not we can combine it. We can't combine that. It's just going to be 1 plus the natural log of 5. And then I can divide that. So because I want to solve for x, I just divide by 3. So I got 1 plus the natural log of 5 divided by 3. So that would be the solution on that particular problem. In both of these cases, they may ask you to approximate it, in which case you would then plug these results into your calculator and get the decimal. Remember, on the AP exam, if they do want you to get a decimal answer, or if you are doing something with your calculator, remember to always give your answer to 3 decimal places. Round it off to 3 at the very least. You can give more. It's okay to give more than 3, but if you give less than 3, then they will not give you credit for those problems. So always get in the habit of rounding off to at least 3 decimal places. The next ones are looking at solving the logarithmic equations. In this case, we'll look at the natural log of 3x minus 4 equals 5. And what I'm going to do there is use the other inverse property that tells me that e raised to the natural log of 3x minus 4 equals e to the 5th. And because of the inverse property, that tells me that 3x minus 4 equals e to the 5th power, in which case now I can add 4, so I get 3x equals e to the 5th power plus 4, divide that by 3, and I get x equals e to the 5th power plus 4 divided by 3. Now I can put this into the calculator again, and I think in the books, in some cases, they will give you the decimal answer on this one, but this right here would be the exact solution. So that's how we went through on this particular problem. What I would like you to do now, I want you to pause the video, and I would like you to solve this other equation, the natural log of x minus 4, that quantity squared, equals 12. So pause the video and solve that problem, and once you're finished, you can come back and we will go over the solution on one solution for this particular problem. Welcome back. The solution to that second problem should have been that x would be equal to e to the 6th power plus 4. Let's take a look at how this particular problem was done. One way to do this one, and the way I tend to approach it, is to start out with, because we have that squared right there, I have a property on logs that tells me that that exponent can be brought out in front. So that's what I did there. I brought this 2 out in front. So I had 2 ln of x minus 4 equals 12. At this point, I want to get the natural log by itself, so I divided by 2. So when I divided this by 2, I had the natural log of x minus 4 equals 12 divided by 2, which would be 6. At this point now, I'm going to go and write this as an exponential. So I got e raised to the natural log of x minus 4 equals e to the 6. And because of this inverse relationship here, I have x minus 4 equals e to the 6th power. I add 4 to both sides, and I get x equals e to the 6 plus 4. Now, one question I'm sure that has come through, has come up a few times now as you've looked at this, and people do ask me this: do you have to go through and do this particular step? And the answer is no. You know, if you remember from last year, we did something very similar when we solved these things with the logs. We rewrote it in its exponential form, and so it is fine, and I would not have a problem if you went from ln of x minus 4 equals 6 to x minus 4 equals e to the 6, if you skipped that middle step. Now that we've done some stuff with solving and using those properties with natural logs and the natural exponential, and we've already dealt with the derivative of natural log, you've been dealing with that the last few days with the derivative and integral of the natural log, we now need to get to the calculus of e to the x, okay? And so what I'm going to do on this one, to find the derivative of the natural exponential function of e to the x, I'm going to use logarithmic differentiation. And so I wanted to find with e to the x, y equals e to the x, so I have y equals e to the x. Logarithmic differentiation tells me that I just take the natural log of both sides. So I have the natural log of y equals the natural log of e to the x, which we know by our inverse relationships that the natural log of e to the x is just x. So what I now have is that the natural log of y is equal to x. At this point, I'm going to take the derivative. And I use implicit differentiation. I know that the derivative of the natural log of y is going to be 1 over y times dy dx. And that is going to equal the derivative of x, which is 1. When I solve that, I get that dy dx is equal to y. And therefore, we know if you look up above here, we know y equals e to the x. And so therefore, I can say that the derivative of y with respect to x is equal to e to the x. In other words, this is my favorite differentiation formula. I know that the derivative of e to the x is e to the x. And I know that the derivative with respect to x of e to the u is equal to u prime times e to the u by the chain rule. I hope you can see why I say that this is my favorite integration or my favorite derivative formula. It's because it is pretty easy. So it's an easy one to remember. It is a function whose derivative, e to the x, is a function whose derivative is itself. Let's take a look at a couple examples. In this case, we want to find the derivative of 5 times e to the x squared plus 5. Okay, what I have to do, what you have to remember here, is that I need to apply the chain rule. And I know that when I take the derivative of e to the u, it's going to be that u is the exponent. It is going to be, the answer is going to be the derivative of the exponent times the e to the u. So when I look at this particular problem, where I have y equals 5 e to the x squared plus 5. The x squared plus 5 is part of the exponent. I know that dy dx, because this 5 here, that constant is just, it's a constant, so it's going to be 5 times e to the x squared plus 5 times the derivative of the exponent. Well, the derivative of x squared plus 5 is 2x. And so in this case, dy dx for 5 e to the x squared plus 5 is going to be 10x e to the x squared plus 5 power. When I take a look at the second problem here, y equals x squared e to the negative x. All right, in this case right here, you have a couple things you have to be aware of. You've got to be aware of the fact that you do have a product. So the product rule comes into play on this one. So I know that when I take the derivative, dy dx is going to be the derivative of the first. Well, the derivative of x squared we know is 2x times the second, which is e to the negative x, plus the first x squared times the derivative of the second. Now this part you got the chain rule that comes into play as well. May not look like the chain rule, but you do have the chain rule. In this case, it's going to be the derivative of e to the negative x is going to be e to the negative x times the derivative of that exponent, which is negative, which the derivative of negative x is going to be negative 1. And so what I get with this one is that dy dx is equal to 2x e to the negative x minus x squared e to the negative x. Now let's take a look at another problem. And this is a problem that is also in your book. We want to find, we're going to let capital F of x equal the integral from 0 to e to the 2x of the natural log of t plus 1 dt. And what they want me to do is they want me to find the derivative. In other words, I know that f prime of x is going to be the derivative with respect to x of the integral from 0 to e to the 2x of the natural log of t plus 1 dt. Now to do this problem, we need to apply the second fundamental theorem of calculus, which really just tells us that we have to do two things when I take this derivative. First up, the t here is going to be replaced with this particular function here. And you do have to remember, you've got to treat this as the inside function, so we do have to take we do have to multiply the result by the derivative of that. So in this case, I know that f prime of x is going to be the natural log of e to the 2x plus 1, put the e to the 2x in place of the t, times the derivative of e to the 2x, which is going to be times e to the 2x times the derivative of the exponent, which is going to be times 2. So f prime of x is going to be 2e to the 2x times the natural log of e to the 2x plus 1. And that would be our derivative of that third equation right there. Now let's take a look at the integration of exponential functions. Well, we already know that the derivative of e to the x is e to the x. So it makes sense that when I integrate e to the x with respect to x, that I would get itself, e to the x plus c. The other thing you have to keep in mind when we have, again, the chain rule, the idea of the chain rule comes in, so a substitution may be necessary. And so when I integrate e to the u du, that will be e to the u plus c. Let's look at a couple of examples that we have here. In the first example, I want to integrate e to the 1 over x squared power and that whole thing is over x cubed with respect to x. So in this particular problem, what I'm going to do is I am going to let u equal 1 over x squared, which again is x to the negative 2 power. And then du is going to be negative 2 x to the negative 3 dx, or negative 2 over x cubed dx. Well, you notice that we have the x cubed there. I don't have the negative 2. And so when I do that, what I can do is I can put the negative 2 in here. And if I put a negative 2 in there, I have to have a negative 1/2 on the outside because the negative 1/2 times the negative 2 would cancel each other out. And so when I make that substitution now, this is going to be negative 1/2 times the integral of e to the u du. The negative 2 over x cubed is the dx is equal to du, and so it's just e to the u du, which will be negative 1/2 e to the u plus c, or our final answer would be negative 1/2 e to the 1 over x squared plus c. That would be the integral of that first function. Now let's take a look at the second function I have here. The integral of e to the 3x times cosine of e to the 3x dx. In this case, we do have a substitution that we need to make, but unlike what we did in this first problem where I let u be the exponent, in this case really the u is going to be the e to the 3x. So I'm going to let, in this case, u equal e to the 3x. So du is going to be the e to the 3x times the derivative of the exponent is going to be 3e to the 3x dx. And again, like in the first problem, we don't have the 3, we have the e to the 3x. So I need to put the 3. I'll add a 3 in here. And to compensate for that, I'll put a 1/3 on the outside. So that the 1/3 and the 3 cancel each other out, gives me 1. And so when I make the substitution, that's going to be 1/3 times the integral of the cosine of u du. The 3 e to the 3x dx, that is equal to du. So that covers that. And then this was just u. And so when I integrate cosine, the integral of cosine we already know is equal to sine. So that's going to be 1/3 times the sine of u plus c, or 1/3 sine of e to the 3x plus c. And that would be the antiderivative of that particular problem. This now does conclude the video, the notes for section 5.4. We will do a couple of more examples in class, and then we will spend time working on the problem set for that. Remember to identify any questions that you have from this particular video, and make sure to ask those in class. And with that, I hope you have a good evening, and I will see you at our next class.